All right, it is Tuesday, October 20th, 2020, and we'll be completing section 2.1 from the text about describing location in a distribution. So we'll review percentile and z-score and talk about transformations. All right, so here we go. First, the review of percentile. Percentile tells you the percent of observations less than the observation being considered. All right, for example, if you scored a 75 on a test and you are at the 95th percentile, then you scored better than 95% of the other students who took the test. All right, 95% of the students scored less than a 75. This also means that 5% of the students who took the test scored the same as you or higher. All right, if 95% scored a 75 or lower, 5% scored better than a 75 or 75. All right, we have that equal to part. All right, so this is percentile. This is what we did last week. Is there anything I can clarify on percentiles? All right, can you raise your hand if you need another moment to write any of this down from this slide? Okay. All right, next we have the standardized score or z-score. Standardized score describes how many standard deviations a value is from the mean. So it relates all of our values back to the mean. A z-score is positive if the value is greater than the mean, meaning to the right of the mean in the distribution. And a z-score is negative if the value is less than the mean or to the left of the mean in the distribution. You can standardize a score with this formula. We use the z equals x minus x bar divided by s sub x. These letters all have a meaning. Remind us what they are. All right. The x here is an observation. It's one of the values from our data set. The x bar, right here, this is the mean of the sample. And the s sub x, this is the standard deviation of the sample. And we have to say that the x bar and the s sub x are from a sample, because that's what those notations mean. It means that this data is a sample from the population. So we have the sample mean and the sample standard deviation. If we had all of the data from a population, we would have to use different notation. The same formula, but we would replace x bar and s sub x with the variables that represent the mean of the population and the standard deviation of the population. And in that case, it would look like over here. Z, we'd still use Z equals x minus mu, that little Greek letter, mu divided by sigma sub x, the little O or zero looking thing with a tail on the top, that is sigma, lowercase sigma, all right? And with these, right, mu represents the mean of a population. Okay, so that means I have sampled everyone in the entire population that I'm curious about. I did not leave anyone out. This would be the mean of the population. If I have the mean of the population, that means I can get standard deviation of the actual population. And that's what this symbol represents, the standard deviation of the population. Okay. The calculation is exactly the same. It's just we have to be careful with the notation that we use because they do have special meanings. All right. Any questions about these formulas or the standardized score? Right. If you need a moment to write anything down from this slide, can you raise your hand? All right. So then we can compare data using z-scores. Right? This is one of the advantages of a z-score. So in our scenario here, we have a student who scored an 86 on a first test and an 82 on a second test. The mean of the first test was 80 with a standard deviation of 6.07. The mean of the second test was 76 with a standard deviation of 4. We want to answer the question on which test did the student perform better on relative to the class. Right, and it's easy to just assume that the student did better on the first test because they got an 86 on the first one and an 82 on the second, and 86 is bigger than 82. However, we want to consider essentially the difficulty of the test. Right? Based on the mean or the average score on the test, it would seem as though the second test was more difficult than the first test, because the second test had a lower mean, right, and a lower standard deviation. All right, so we're going to calculate our z-scores and see, based on or compared to the rest of the class, did this student do better on the first or second test? So we'll look at the first test. All right, and our z-score on the first test is going to be 86, the score minus the mean of 80, divided by 6.07. And this will give us a z-score of approximately 0.99 after doing the math. And then on the second test, we will get a z-score that is equal to 82 minus 76 divided by 4. And this will give us a z-score of 1.5. Based on this result, the student performed better on the second test relative to the class. because the student's score was 1.5 standard deviations greater than the mean, as opposed to on their first test, they were only about 1 standard deviation greater than the mean. In both cases, they were above average, right? However, they were essentially more above average on the second test than the first test, based on the standard deviations and the z-score. Okay? So relative to the class, the student performed better on the second test. And we can make a statement to that. Let's say relative to the class. The student performed better on the second test. All right. What can I clarify? What questions do you have? Okay. Does anyone need another moment to write anything down from this slide? Okay. Don't see any hands. All right, so next we're talking about transforming data. We've already seen a transformation of data, and that's with the standardizing scores. All right. This is one way to transform our data. We're converting it from a test score in our previous example to the standardized score, which really makes it relative to the mean, right? How far from the mean is my score? Transforming data allows you to change the units of measure to make comparisons easier. If I can convert things to the same unit of measure, right? If I can convert things to a z-score, I can compare things that would have otherwise not been possible to compare. Right? I can compare things that are measured in entirely different units. Right? This could be seen like an example would be comparing ACT and SAT scores. The SAT and the ACT are scored on different values. The ACT, I think, is out of like 35. So the range of scores can be from like 0 to 35, but the SAT is scored out of 1600. They're both college readiness exams, right? And they both kind of test on the same content, but they're scored entirely different. So I can't just compare the raw scores. I can't compare the raw data. It doesn't work out. But if I convert those into z-scores, for example, and compare someone's scores, people's scores based on how many standard deviations there are from the mean, I can compare those things because now they're in the same unit. Another example would be comparing distances between kilometers and miles, right? Those are not the same unit, but I can convert them to make them the same unit. That's a transformation of the data. Comparing grades from percentages and 4-point scales. Percentages and 4-point scales aren't the same. It doesn't make sense to compare a 3 to an 80%. They don't mean the same thing, but if I then convert these to z-scores, for example, that's kind of the easiest one to go to here, I can kind of compare someone's results. All right, so the transformation allows me to compare data that otherwise I wouldn't be able to compare. All right. You raise your hand if you need a moment on this screen to write anything down. So we're going to look at an example, transforming data. Right here we have a dot plot, and it represents students who guessed the width of their classroom to the nearest meter. Their guesses are displayed below. So when we have our summary statistics to go with this, the guesses ranged from about 8 meters to 40 meters. Big range, right? A lot of data points here. We have 45 students who guessed. Okay, so we have this distribution skewed to the right. We have the median is at 15. Right, mean is almost the same at 15.8, just a little bit higher. So here we have that. Now, we've transformed this data by taking our original guess in meters and calculating the error of each student's guess, and then plotting that on a dot plot as well. To calculate the error, what we did was took the student's guess and subtracted the actual room width to determine how far off they were. Right? So if you actually guessed the room width correctly at 13 meters, which is what it ended up being, then you had an error of 0. Right? So those students were right here at 0. There's 3 students who guessed correctly. Right? If you guessed 8 meters, right, that was too low. When you subtract 13, you get a negative number, right? We ended up at -5 here. Right? So that's how this dot plot above was determined. What do you guys notice about these two dot plots? What is the same and what's different? What stayed the same and what changed?
The gaps are different.
Okay, the gaps are different. What do you mean by that?
Like, there's, like, for the first one, there's 15, and then there's a gap to, like, 20, I want to say 23. And then on the second one, there's a gap to, like, yeah, right there, and then all the way to 35. And it looks like the left side of the distribution is almost the same as the top one. But if you see at the bottom, the outliers kind of look the same-ish. I don't know.
Yeah. So, excellent. Right. And so, yeah, Elliot was kind of, and Raul were touching on the same things. The numbers shifted, right? So where everything was changed, right? So we can kind of say like, what changed? Like location, right? Where everything was changed, right? Stayed the same, the shape, right? We still have the same shape on both graphs. They look the same. I could put one on top of the other and it would be the same, right? So the shape of our distribution stayed the same. What changed? Location of numbers, right? The location of like the mean and median between the two graphs changed, right? Is the range different between these two? If I calculate the range for each graph, will it be different or the same? Yeah, we have -5 here, and we go to, go ahead.
Oh, I just said different.
The range will be different, okay. So let's calculate it. To find the range, right, we do the maximum minus the minimum, right? So the range on here is going to be 27 minus -5, or maximum minus the minimum. It's going to be 32. Range here, we're going to have 40 minus 8 is also 32. This shows that the range, right, the value of the range, right, how much units we go from the smallest to the largest is the same. This also means that our interquartile range will stay the same. As far as the value between Q1 and Q3, the number of units between those two is going to be the same between both distributions. Right? What changed is location, right? Location of the mean, the median, right? The quartiles. The locations of these things all shifted based on the fact that we subtracted 13 from everything, essentially. Right? So, in a nutshell, when we add or subtract a constant, and the constant is just a fancy math way of saying a number, like a whole number, adding the same positive number or subtracting, right, to each observation adds a to or subtracts a from measures of center and location, right? Mean, median, quartiles, percentiles. Right? So the measures of center and location of specific points, quartile, median, those types of things, they're all going to shift based on whether we're adding or subtracting. It does not change the shape of the distribution or measures of spread, the range, IQR, and standard deviation. Right. So adding, right, if I transform my data by adding a number or subtracting a number, it will change the measures of center and location, but will not have any effect on the shape or the measures of spread as far as the values of the measures of spread, range, IQR, and standard deviation. What questions do you have? All right. Can you raise your hand if you're writing this down? Yes. All right. So next, we're going to look at the effect of multiplying or dividing by a constant. The same group of students, they're now converting their error data to feet rather than meters. That unit measure is more familiar to them. Here is their new data compared to the original error data. So we have our original error data on the top here, error in room width guess in meters. And we have our error in room width guess in feet. What stayed the same? What stayed the same between these two? Yes, it always says the shape. That is correct. Right. The amount of data points stayed the same, yes, but their values, if you look, while they look the same, because the like size, as far as like zooming of the graphs looks the same, the values on the horizontal axis are different between the two. All right, so like comparatively, right, the two endpoints, this one's at 27, this one's at like 89. All right, so our values have changed, but our shape has stayed the same. When you multiply or divide your data by a constant, the shape is the only thing that stays the same. Everything else gets shifted around a little bit, right? Because we're multiplying or dividing. So again, it might look the same, but we need to pay attention to the numbers along the bottom of our line here. Okay. In a nutshell, right, we are multiplying or dividing each observation by the same positive number b, multiplies or divides measures of center and location, mean, median, quartiles, percentiles, and multiplies or divides measures of spread, range, AQR, standard deviation by b. Right. The only thing that does not change is the shape. Everything else gets kind of scaled up or scaled down depending on if you're multiplying or dividing. Right. In our example case, everything got bigger, right, because we multiplied by a number greater than 1. Okay, so we can add or subtract a constant, we can multiply or divide a constant. No matter what we do to transform it, the only thing that always stays the same is the shape. If I'm adding or subtracting, our measures of spread stay the same as well. Then our measures of center and location will change. When I multiply and divide, measures of center, location, and spread all change. What can I clarify? All right. Can you raise your hand if you need more time to write this down? All right. Let's look at some examples using our transformations. All right. So essentially, transformation is going from one unit of measure to another, or converting our data in some way. So we have these two examples. Let's look at our first one. When Sam goes to a restaurant, he always tips the server $2 plus 10% of the cost of the meal. If Sam's distribution of meal costs has a mean of $9 and a standard deviation of $3, what are the mean and standard deviation of the distribution of his tips? So let's look at our data. All right. So we have $2 plus 10%. Got a mean of $9, standard deviation of $3. And we now need to convert that to the mean and standard deviation of the tips using the fact that we're adding $2 and multiplying by 10%. So if we think back about our mean, the mean, right, measure of center, will change when we add and when we multiply. So I need to do both operations to the mean to get my new mean for tips. All right, we need to do the addition and the multiplication because those both have an effect on the mean. So if we start at $9, we have to multiply that by 0.10 for 10%, and then add the $2. Right, the 10% of $9 tells us how much then we get to add $2 to determine the tip. This results in a $2.90 mean for the tips. So this is the X bar for the tips. The standard deviation does not change when we add value to it. Right? Adding a constant does not change the standard deviation. So with the standard deviation, I only need to worry about multiplying to find the new standard deviation. So that means I take the $3, multiply by the 10%, 0.10. We get 30 cents as the standard deviation for the tips. Right, that means that typically, right, the tips vary from the mean by about 30 cents, either 30 cents higher or 30 cents lower. So that's how we can use this idea of transformation to find a new mean and new standard deviation. But we need to understand which one has what operation has an effect, right? What questions do you have? What can I clarify? What's not making sense? Okay. Let's look at our other example. Right, scores on the ACT college entrance exam follow a bell-shaped distribution with a mean 18 and standard deviation 6. Wayne's standardized score on the ACT was a negative 0.5. What was Wayne's actual ACT score? Okay, so in this case, we're going back from the standardized score to the actual score. So we know that we have a mean of 18. And then we have our standard deviation of 6. And our standardized score was 0.5, which means Wayne's score is smaller than the mean. Right? And it's half of a standard deviation smaller. We can find this by doing the calculation and just setting up the z-score with the information we have. So we know that it's 0.5, negative 0.5 equals whatever Wayne's score was, x, minus the mean of 18 divided by 6. So that's how we would calculate it. The only thing we don't have is x, right? So we solve for x. Start by multiplying by 6 on both sides. Okay. When we do that, the 6's here cancel. We have 6 times the negative 0.5. That will be a negative 3. And that equals x minus 18. Add 18 to both sides to cancel out the 18 that's along with the x. And we have negative 3 plus 18 equals 15. And that equals x. That means that Wayne's actual ACT score was 15. All right. And so we can use just kind of like understanding what a transformation was, right? We know how to calculate a z-score. So if we're given a z-score, we can kind of work backwards to get to an original score or an original value. And like in our first example, knowing which operations have effects on which numbers allows me to determine new values, right, based on the context. Okay. What other questions do you guys have? What can I help you with? All right. Well, that is the lesson for today. Talking about z-scores, percentiles, right? And transformations. That is it. Next class, we'll talk about density curves. Oh yeah, very exciting.